In Chapter 8, we're going to start learning about alkenes and the reactions that they undergo and how to make them from other compounds. If we look at the alkenes, we're going to see they have a functional group that allows them to be converted to other compounds, and that other compounds can be converted to the alkenes. When we first started talking about functional groups, I informed you that functional groups were a point at which organic compounds can react. And so what's really interesting is because they have a high energy bond, the alkenes have a pi bond that's high energy, it lets them be susceptible to reactions that convert them to other functional groups. And so what we're going to do is see how they can undergo all those reactions. We are going to learn how to form alkenes from some other functional groups. First of all, we're going to look at how to form an alkene from an alcohol compound. Notice we can take an alcohol and remove water, hydrogen, and the alcohol group. Notice they're on adjacent carbons so that you can get a double bond. They have to be on adjacent carbons. And you will be able to form this double bond by removing the water. How is it that we remove the water? We use a dehydrating compound. That dehydrating compound is something like concentrated sulfuric acid. Concentrated sulfuric acid has a great desire to pull water into itself and dilute itself down. So when you mix an alcohol with concentrated sulfuric acid, it will dehydrate it by pulling water off and forming a double bond. Another way to do this is to take a halogenated alkane and treating that halogenated alkane with really strong base. Notice, if I take the hydrogen off here and the halogen there and combine them, it looks like an acid, right? Well, it is. So if we treat if we treat a halogenated compound with strong base, it removes that acid portion of the molecule to form a double bond. Notice it's a hydrogen on an adjacent carbon to a carbon that has a halogen on it. The type of strong base that we use is something, we call this right here, sodium ethoxide. It's an alcohol group that has been treated with something to change it into a really strong base. Potassium hydroxide in ethanol also works. It's a good strong base. Potassium hydroxide is stronger than sodium hydroxide. And here's an even better one. This is called potassium T-butoxide. Notice there's carbon, 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 carbon. This is a T-butyl group. And it's got an oxygen here that used to be an alcohol, but it's been treated with potassium to change it into the conjugate base. See, this is the conjugate base of ethanol. This is the conjugate base of T-butyl alcohol. And both of these are very strong bases. This one is a really hindered base too, which we'll see later on in another chapter, that this is really helpful in forming an alkene. Later on, we're going to study in more depth about the regioselectivity of the reaction. Regioselectivity means where does the functional group end up? And what we will see is the more substituted double bond is usually formed, since it's lower in energy, it's more stable, so the reaction heads that way more easily. We're going to understand this in greater depth later on. Right now, I'm just going to expect you to understand that the more substituted double bond forms. Okay, it's the formation of a more stable product is really important when we look at reversible reactions. But again, we're going to be studying that in greater depth later on. Here is an alcohol, and notice there's the alcohol group. We're going to form a double bond because we're treating it with heat and acid. Notice we'll just say this sometimes, even though we will use sulfuric acid a lot of times, concentrated sulfuric acid, but that's just saying acid and heat. Okay, if we look, the alcohol group is on this carbon. So to form the double bond, what do we have to do? We have to go to an adjacent carbon and get a hydrogen in addition to the alcohol group, so we're removing water. Notice we're not going to this carbon nor to this carbon, and we can't even go to this carbon because that's too far away. It has to be an adjacent carbon, but we're not going to this one nor this one. Why? Because if I put the double bond here, it's a less substituted double bond than here. And the more substituted double bond is formed. So when I look at the product, what do I see? I see that there is a double bond, so that this is a tri-substituted double bond, rather than if I put it over here on these two carbons, it would be a di-substituted double bond. So the tri-substituted is more favored, and that's primarily what is formed. So let's try these problems. What alkene would form when I treat these with acid to dehydrate them? Okay, if I look at this first compound, you can see the double bond will have to be attached to this carbon because the hydroxyl is there. Now, where will the double bond go? Can it go this way? Well, let's look and see if that carbon has a hydrogen it can lose. There are 3 bonds on it, so yes, there's a hydrogen there. Can it go this way? Well, that carbon has 2 hydrogens on it. But if I go this way, it's going to have less substitution on it than if I go this way. So the product that forms is going to have the double bond here between these 2 carbons. If we go to this compound, we can see the double bond is going to have to be on this carbon and either extending to this side or extending to this side. Which way will it go? Well, if we take this hydroxyl off, and we're going to have to take a hydrogen off to form water, so we'll have to take a hydrogen from this carbon, and that would form a monosubstituted alkene. But if I go ahead and I take the oxygen and hydrogen here and then a hydrogen over here, I would get a double bond in here, and that's disubstituted. So the product that forms would be more substituted, and so would have your double bond between these 2, which is these 2 carbons. Okay, try to figure out what alcohol would you need to make these. From what alcohol would you use to treat with sulfuric acid or concentrated phosphoric acid to get either of these compounds? Okay, if we look at this first one, we know the alcohol group has to be either here or either here. So there's really 2 possibilities. If I have it here and I dehydrate, it's not going to go here and it's not going to go here. It will go there. But likewise, even if I have the alcohol group here, it won't dehydrate this way. It will dehydrate this way. So really either compound would be acceptable. If I look at this compound, what alcohol would you want to have beforehand? Well, you can either have it here or you can have it here. If I have it here, the alcohol there, I would find it's not going to dehydrate this way. It's going to go more substituted and make it here. However, if I put an alcohol group here, it's more substituted to go this way. So you cannot have the compound where the alcohol would be right here. This is the only answer for that problem. Okay, now we're going to look at removing something like hydrobromic acid or hydrochloric acid from a halogenated compound to make the alkene. Notice, when I use a strong base, it's going to basically remove acid, the hydrogen and the bromine on adjacent carbons to form a double bond between those. And just like with the alcohol, we're going to form the more substituted alkene. Okay, what alkene would form when we treat these compounds with strong base? Well, this is going to be very similar to the alcohol problems. We identify the carbon that has the halogen on it, and then we identify the adjacent carbon that would give a more substituted alkene. And this would be the product of that reaction. Likewise here, we identify the carbon with a halogen on it, and then we identify the carbon that has a hydrogen on it that would give the more substituted alkene. And that is the product of this one. So what did you learn? Alkenes are formed from alcohols and from halogenated alkanes. To form an alkene from an alcohol, you treat with strong acid and it removes water. The alcohol group comes off and an adjacent carbon loses a hydrogen and you form a double bond between those two carbons. Halogenated alkanes are treated with strong base to remove acid, basically, like hydrobromic acid or hydroiodic acid or hydrochloric acid. That strong base removes the acid, and what you have is a halogen comes off one carbon and an adjacent carbon loses a hydrogen, and you form a double bond between those two carbons. So this is very straightforward and simple, but you do need to practice problems on this or you will not be able to do these problems. So be sure and go and practice some problems on this in your book. There's some within the chapter that the in-text problems right after the section that covers this. Do those problems.